Hi everyone, my name is Jingze Zhu. I'm glad to talk in this Geometric Analysis Festival. First, I want to thank Professor Hojo Lee for his organization and invitation. In this talk, I will begin with some introduction to the mean curvature flow, and then I will talk about my recent results concerning the symmetry of the translating solitons. Let's begin with some introduction. So, the mean curvature flow is a family of immersions that moves by the mean curvature. These immersions are from the n-dimensional smooth manifold M to Rn plus 1. For abbreviation, we would write MT to be the image of these immersions. It's not necessary to define the mean curvature flow to be embedded or immersed in Rn plus 1. We can have higher codimension definition, but for simplicity, we will only discuss about the codimension 1 mean curvature flow here. Let's talk about some examples. The easiest one is that MT equals the static Rn. More generally, we can let MT to be a static minimal surface. The second example is that MT is the shrinking sphere, and the radius is given by root r squared minus 2nt. Then we have the shrinking cylinders. They are just the shrinking spheres crossed by some r factors. The last example I want to mention is the Bose-Soliton. It is a graphical solution and could be expressed as a graph of function h plus t. This solution is rotationally symmetric, and therefore this function h only depends on the radius of x. And you can see from this expression that this solution is moving upwards at the constant speed. This h will be determined by a second order ODE with initial condition h0 equals 0 and h prime 0 equals 0. So the Bose-Soliton looks like this. Next, let's talk about the embedded solution. Remember that if a hypersurface is embedded in Rn plus 1, then there is an open domain Kt that is bounded by Mt. In other words, the boundary of Kt is Mt. We also want to require that if Mt is compact, then Kt is the bounded one. With the choice of Kt, we can then talk about the inward pointing normal vector denoted by nu, and then the mean curvature vector is unambiguously written in this form. So then the mean convexity is defined to be h bigger than or equal to 0. And so in particular, the mean convex solution is embedded mean curvature flow solution with non-negative mean curvature. Now the evolution equation for the mean curvature is given by this equation. This term, a squared h, has a positive or at least non-negative coefficients. Therefore, the maximal principle apply, and the mean convexity is preserved along the flow of closed hypersurface. This means that if we start with a hypersurface with non-negative mean curvature, then it keeps being so along the flow. I should remark that embeddedness also has this is also a preserved property, which means that if we start with an embedded hypersurface, then along the flow, the surface is always embedded. This is also proved by the maximal principle For example, we can assume that T is the first time that it fails to be embedded. Then at time T, the surface must have some intersection, and the intersection is actually tangentially. So the picture should look like this. But then we have, we can write the surface as a graph near this contact point and use some maximal principle to show that actually these two surfaces touched at an earlier time. So that's a contradiction. From now on, we will focus only on the mean convex mean curvature flow solution. Now, let's mention a more general convexity condition. So note that the second fundamental form A is a self-adjoint linear map on the tangent space, also known as Wing-Gordon map. And the eigenvalues are denoted by lambda 1, lambda 2 to lambda n in the ascending order. They are called principal curvatures. In particular, the mean curvature is the summation of all the principal curvatures. And we define the k-convex or uniformly k-convex solution to be the mean curvature solution that satisfies the lowest k principal curvatures is bounded below by beta times the mean curvature for a fixed beta. So in the k-convex case, we require that beta is greater than or equal to 0. And in the uniform like k-convex case, we require that beta is greater than 0. So this condition is getting weaker when k is becoming larger. For example, uniformly 1 convex means that it's uniformly convex, while uniformly k-convex is a vacuous condition. We can see that the uniformly k-convex condition is also preserved by the flow because the evolution of the curvature tensor. This equation looks exactly like the equation for mean curvature, and therefore we can apply the Hamilton's tensor maximal principle to obtain that uniform k-convexity, or the k-convexity is preserved along the flow. So far, we have discussed about some preserved property of the mean curvature flow of closed hypersurface. Then we want to go to some special solutions. The first one we want to mention is the self-similar solution. They satisfy this property, which means that they shrinks homothetically. And suppose that capital T is 1, then the M0 actually satisfies this equation, h equals a half x dot nu, where x is the position vector and nu is the normal vector. The translating soliton is another special solution that moves by a constant speed, as you can see in this definition. And lastly, we have ancient solution, which is more general and which contains the first two categories. This is the solution that exists on minus infinity to capital T for some big capital T. Our previous examples actually fall into these categories. For example, the shrinking sphere and cylinders are self-similar solution, and the Bose soliton is the translating soliton. And of course, they are all ancient solutions. So why they are important? That's because of an important result, which roughly says that the singularity is modeled on the ancient solution. And this ancient solution actually satisfies that they are convex and non-collapsed. We will make these statements more precise after some definitions. So the first thing is the basic of the singularity. So it's well known that the singularity must occur within finite time. The reason is that we could construct a sphere that bounds the original surface. And then there is the avoidance principle, which says that if two surfaces or two solutions of the mean curvature flow are disjoint initially, then they keep being disjoint. So if we draw a big sphere outside our mean curvature flow solution, could even be immersed, then the outside sphere would shrink within finite time. It will become a point. So that means our solution cannot exist forever. It has to stop existing before this sphere shrinks to a point. Okay, here is the proposition, which says that the second fundamental form actually should blow up near the singular time at this rate. So this could be obtained by writing down the evolution equation for the second fundamental form. And this capital T is called maximal existence time. So yes, as said before, we want to make some definitions. So the first one is the alpha non-collapsedness. So a mean convex hypersurface is said to be alpha non-collapsed if it bounds an open domain, and if for each point in M there exists two balls with the radius at least alpha times the mean curvature inverse, and the one ball is contained in the open domain bounded by M, and the other ball is contained in the exterior of that open domain K. And also the point should lie in the closure of these two balls. So the picture should look like this. We have a mean convex hypersurface, and therefore it's embedded, and there is an open domain K, which is bounded by it. And then, for example, at this point P, we can fit in the ball 1 and ball 2. So in the smooth case, they are actually tangential to the hypersurface. So these two balls should have the radius at least alpha h inverse. This is roughly the picture. This quantity, which is multiplied by h inverse, that was designed to make this entire picture scale invariant, which means that if I dilate the picture by a factor of lambda, then the radius of these balls will be dilated by the factor of lambda, whereas the mean curvature is dilated by lambda inverse. So this h inverse exactly dilates by a factor of lambda. Now, let me describe some scenarios in which the alpha non-collapsedness can fail. So this theorem tells that alpha non-collapsed property is actually preserved. But I just want to mention how that could possibly be failed. So the first picture is a local picture. If we have a saddle point, for example, and then we have a huge principal curvature here, which is in this direction, and we also have a huge negative principal curvature, and somehow they offset each other, gives a reasonably small mean curvature, but they have huge principal curvature, and then the ball we can fit in has to be very small, like this. And therefore, if the principal curvature gets larger and larger, whereas the mean curvature doesn't become very large, then the alpha non-collapsed property will eventually fail. The other picture is more like a global picture, where we don't have crazy behavior at one point, but somehow the surface goes around, and we can't fitting a ball in this tiny space. So suppose that, for example, we can make a clearer picture that if we have two sheets that are close to flat, but they are very close to each other, and then the mean curvature is tiny, so this quantity will become huge. But since they are very close to each other, we can't fit in a huge ball. So that way, the non-collapsed property will also be failed. Then this theorem tells us that this property actually doesn't fail, which means that suppose if we start with strictly mean convex smooth hypersurface, then by smoothness, there must exist some small alpha such that the initial hypersurface is alpha non-collapsed. And then by this theorem, we would always have alpha non-collapsed property along this flow until the singularity. So this is quite remarkable. So I should mention that this result could be indirectly obtained by the result I wanted to mention later. And these are the main theorem or the very important results in the regime of mean convex mean curvature flow. But this result by Andrews is proved in a very elegant way. Namely, he used the maximal principle only and doesn't really rely on a lot of blow-up analysis. So this is quite remarkable. Next, let's define the limit flow. Given a mean curvature flow solution MT, we can always do a parabolic dilation, which is given in this form. We can check that this is also a mean curvature flow solution. And then we define it to be the blow-up sequence if the dilating factor mu I goes to infinity and the center point converges to a fixed space-time point. Suppose that the sequence of MTI converge, possibly in the subsequence, then the limit is called the limit flow. Of course, we can define the same dilation for KTI, which is the open domain bounded by MTI. And the formula, of course, is given by this. We also define the space-time track, denoted by this M, to be the union of MT cross T. So this is a subset of Rn plus 1 cross R, where R corresponds to the time direction. In the same way, we'll also define the space-time track for KT, where KT are the open set bounded by MT. Here comes the famous theorem. So this theorem was first proved by Brian White in around 2000 and 2003. And then Xujia Wang was able to give another proof. And then comes the maximal principal proof by Ben Andrews of the non-collapsed property as we have just described. Based on this, Hasselhoff and Kleiner are able to give a much shorter and simpler proof. Here is what it says. Suppose that MT is a mean convex mean curvature flow of closed hypersurface, and MTI are blow-up sequence as we have defined before. And assume that the rescaling factor mu I is at least the mean curvature at xi and ti, then we get that the space-time track will converge smoothly to a limit in the time interval minus infinity to 0. And moreover, the limit is smooth, convex, non-collapsed, and ancient solution of the mean curvature flow. So we could also phrase this theorem in terms of the time slice. So we obtain that MTI converges smoothly to MT infinity, and MT infinity is a convex non-collapsed ancient solution, and it exists at least to time 0. This theorem is quite remarkable because this rescaling really just poses a condition that the mean curvature is at most 1 at a single point, which in this case is just 0, 0, because this space point will be mapped to 0, 0 on the rescaling. So usually if we wanted to get convergence, at least we need some curvature bounds in a bigger and bigger neighborhoods. But this theorem tells us that we actually have curvature bounds given the curvature control at only 1 point. So this is very strong. I should also remark that this is a very brief version of the theorem. What they have proved is much more than this. Now let's talk about some special case of the previous theorem, which was obtained earlier. So the first is that when we have the type 1 solution, then we can have an easier argument. So the type 1 solution is defined to be the solution whose curvature blows up at the rate at most the remaining time to the minus a half. Remember that a times root t minus t at least is greater than c prime for another constant c prime. So type 1 really says that this is the optimal blow-up rate in this solution. In this case, we are able to choose xk and tk to be a constant point where x0 is the singularity and t is the singular time. If the limit flow converges, if we have a limit flow, then we'll call it the tangent flow. So we will choose our scaling factor to be the remaining time to the minus a half. Then it can be proved that the limit flow exists and is self-similar. Moreover, in the mean convex case, there has to be shrinking cylinders or spheres. Now, another case is the type 2. So it just is the complement of the type 1, which means the curvature times the remaining time to the power minus a half goes to infinity. So in the mean convex case, we are able to show that the mean curvature actually blows up at the similar rate as the curvature because of the convexity estimates. So this estimate roughly says near the high curvature region, the solution is almost convex, and therefore the mean curvature is comparable to the total curvature. In this case, we can choose as xk and tk in such a in this following way. So xk and tk are such that this quantity are almost maximal. So note that if we don't subtract 1 over k, then this quantity h squared times the remaining time goes to infinity because of this. So it doesn't make sense to talk about the soup because the soup is infinity. But when we subtract a factor of 1 over k, then this capital T is a little bit less than the singular time. And then the mean curvature has to be bounded for each k. But of course, as k goes to infinity, this quantity goes to infinity. So anyway, this xk and tk are such that almost this quantity are almost maximal. Then we take our scaling factor to be the mean curvature at the space points. And then we can get a limit flow. And more importantly, this limit flow has to be the translating soliton. The proof is based on the rigidity case of the Harnack inequality proved by Hamilton. So having seen the importance of the ancient solution, let's study the structure of the convex non-collapsed ancient solution of the mean curvature flow. So let's discuss one more concept before we can study some classification. The blow down limit is parallel to blow up limit. We still have these rescalings, but we require that the scaling factor goes to 0 and the base point is in a bounded region. So it's not hard to see that the choice of xi and ti doesn't matter. So we can just choose them to be 0 and 0. Then also by the theorem by these people, we can see that any blow-down limits of a convex non-collapsed ancient solution must be self-similar. In particular, there has to be one of the sk cross Rn minus k. And this is included in this category if we take k to be 0. So a priori, we can take different blowdown sequence and get different blowdown limits. But it can be shown that these limits actually are unique up to a rotation. Because of this special structure of the cylinder, we know that it is equivalent to saying that k is the same along or between all these limits. This could be shown by an entropy argument. You can see some results by Cody and Minicozy. Now, let's discuss about the easiest case when we have the maximal convexity, namely the uniform convexity. In this case, we are able to show that the only uniformly convex ancient solution, which are non-collapsed and convex, must be shrinking sphere. We can sketch the proof here by these 3 steps. First, use the uniform convexity to rule out all but one blowdown limit. So the blowdown limit must be the shrinking sphere because all the other blowdown limits are not uniformly convex. And in particular, this would imply that the solution must be compact. Then we can go to the step 2, in which we apply Husking's classical result, which says that a uniformly convex compact solution must converge to a sphere after some scaling. Or in other words, the tangent flow has to be Sn. And then the step 3, we can apply Huskine's monotonicity formula with the heat kernel being sourced at the spherical singularity of the flow that we have proved above. And then we can also show that this monotonicity formula must be equality because the blow down and blow up or the tangent flow are the same object. And therefore, this equality case for the Huskine's monotonicity formula would imply that the flow is self-similar and has to be a shrinking spheres. So next, we want to be a bit more general. So let's talk about the uniformly two convex case. In this case, the classification is also complete. But so the classification in this case is much harder, but this is quite remarkable. Of course, we need a lot more work. So the first one is the easy case, that the solution is not strictly convex. In this case, we have the maximal principle of the curvature tensor. We can use the strong maximal principle, and then we can show that the solution has to split off a line. And then basically this is a dimension reduction. And then we can show that the only possibility is this cylinder, Sn-1 cross R. Now the strictly convex case is much harder. The first work was by Hasselhofer, in which he shows that the translating soliton is unique and has to be both soliton. And then it comes the remarkable work by Brando and Choi, which says that the non-compact ancient solution also has to be unique and has to be the both soliton. Finally, it comes to the work of Anganant, Daskalopoulos, and Session, which says that the compact solution is also unique other than the shrinking sphere. And this unique solution will be called ancient oval. Of course, the uniqueness is up to the translation, rotation, and rescaling. Given this promising result, we wanted to ask what happens in a more general case. Let's say the solution is uniformly 3 convex. It turns out that the picture could be much more complicated. First, there are strong evidences that suggest the both soliton is not the only solution. There should be a lot more solutions. To demonstrate it, let's first talk about a class of solutions that has been proved to exist, although that class of solution is collapsed. So consider a one-dimensional curve, which is a translating soliton in R2. So there is a solution called Grim Reaper, which is collapsed and could be characterized by an ODE. This solution basically looks like 2 parallel lines at infinity. And we can cross this Grim Reaper by a line R and then get a 2-dimensional solution. Now, we can tilt this 2-dimensional object by 2 opposite angles and then try to glue them together and smooth out the corner. To be precise, the picture looks like this. So there are 2 wings of Grim Reaper cross R. And they basically look reflexive. And this solution is called the delta wing and is proved to exist. And actually, it's not a single solution, it's a family of solutions that are indexed by the angle. So this solution, because of the collapsedness of the Grim Reaper, also has to be collapsed. But the way it is constructed is inspiring. Namely, if in the higher dimension we can follow similar process, we can consider, instead of Grim Reaper, a translating soliton in higher dimension. So that was exactly the bow soliton. But the good thing about the bow soliton is that it is non-collapsed. So we can do the same thing, conceivably. But this time, on each wing, instead of having collapsed solution, we will have non-collapsed bow soliton cross R. And also we can tilt these two wings and try to make some angles between them, smooth the corner. And then it is expected that such a solution should exist. Okay, let me add to it. So this is the translating soliton. So it is, of course, ancient. And we expect that this kind of picture is also a translating soliton. So this would suggest that uniqueness should fail. But we can do something. As suggested by the previous work in the uniformly two convex case, we are the first step of proving the uniqueness in that case is to prove the maximum symmetry is attained. So in all this previous work, they have to show that the solution is SON symmetric in Rn plus 1. So in the uniformly three convex case, we should not expect that much symmetry. We should expect at most SON minus 1 symmetry. Because, for example, in R4, this solution that we have described, although has not been rigorously constructed, it is based on a two-dimensional bow soliton in R3, and then did all this gluing process. Then, but the two-dimensional bow only has SO2 symmetry. So this resulting solution should at most has SO2 symmetry. And another simple argument is that the blowdown limit could be Sn minus 2 cross R2. But this guy only has SO a minus 1 symmetry. So that's why we only expect this much. Now, here comes the results. We can actually show that this symmetry will be achieved for the translator in R4. So remember that translator is an important special class of the ancient solution. And also the study of the ancient solution is closely related to the translating soliton. Here is the statement of my recent result, which says that if MT is a translating soliton in R4, so it is automatically uniformly three convex. And this solution arises the blow-up limits, in particular to arise as a limit of Hamilton's blow-up procedure. Then it should have SO2 symmetry. So the SOK symmetry means that there's an SOK action under which the surface is invariant. I should remark that For most of the time, we only use that the solution is convex and non-collapsed. Other than that, there's only one place where we use some additional information from the blow-up. That is, there exists a point that such that the maximum mean curvature is attained. So I want to give a sketch of the proof. First of all, we need to define the notion of the symmetry in a correct way. So this is following the work of Brendel and Troy. This vector field K is normalized rotational vector field if K could be represented in this form, where S is an SO4 rotation and Q is a vector in R4, and J is the matrix looking like this. So it only has two non-zero entries. Note that Jx is a killing field on S1 cross R2, and S and Q just corresponds to the rotation of this standard vector field. And I should remark that S and Q are never uniquely determined, which means that for each vector field, we can always find multiple representations. So for example, the Jx for S1 cross R2, this vector field, since it's a killing vector field, it will not be changed under the rotation around, like the rotation around the S1. But we are able to choose such a rotation and represent it by a non-trivial SO4 matrix S. So then by choosing this S, we can get a different representation of Jx, which is SJS inverse X. But this is really just the rotation along this S1, and this should not be changed. Next, we would define a point in a mean curvature flow solution to be epsilon symmetric to be the following. If there exists a normalized rotation vector field such that it's almost killing vector fields, being precise, it's epsilon killing, or the normal part is very small, and then the rotation axis isn't too large, and these conditions should hold in a fixed large parabolic neighborhood. So this parabolic neighborhood is just the geodesic ball along with its backwards development. So for example, on the cylinder, a geodesic ball around one point should look like this. And then the backwards development is just a dilation of this neck. But the length of this neck roughly doesn't change, but diameter does change. I want to remark that the above definition is scale invariant. So note that the appearance of the mean curvature, and here they are designed to make all the statements and definition scale invariant, because the mean curvature scales like the inverse of the distance, and this rotation vector field actually scales like the distance. The second remark is about this condition. So the reason we have this condition is that we don't want it to have exotic picture. So we do expect that if we have a piece of MT that looks like a cylinder S1 cross R2, and we have a vector field that is very tangential to MT, then we should somehow restrict ourselves to those which are close to JX. But if we don't add this condition, then some weird picture could happen. For example, on S1 cross R2, we have the S1 fiber on each point of R2. And Jx is just the rotation along this fiber. But now we can also choose a different rotation vector field, which rotates the R2 vector. So this is not what we want. But this bad vector field does have huge norm, which means it will violate the second condition. So with this condition, we are able to rule out all the exotic picture that we don't want to see. Now, here is the key ingredients, the symmetry improvements. There are two of them. The first one is the generalization of the neck improvements in Brendel and Choi's work. This roughly says that there exists a small epsilon 0 and a large constant L0, such that in a huge parabolic neighborhood of size L0, if this neighborhood looks epsilon 0 close to S1 cross R2, and every point in this neighborhood is epsilon symmetric, which was defined before, then the center point has a better symmetry. The idea of the proof is to make such an observation. This function u equals k dot nu, where k is some rotation vector field. It satisfies the following Jacobi equation. And this equation will modify most of the modes. But the bad modes could be handled by the adjustments of k. Let me outline the proof of this lemma. First, we set us up by using the polar coordinates theta z1 and z2. So to give a sense to you, under this coordinates, S1 cross R2 should be the set cosine theta sine theta and z1 z2, where theta is in 0 to 2 pi and z1 z2 is in R2. And then we have this modes B1, which looks like this. It is very explicit. So this family of solutions are the solution to the Jacobi equation on cylinder. They would correspond to the tilting and translation of the axis of k. That means if we modify k a little bit by k tilde, then the resulting k dot nu will roughly be changing by this B1 and add some higher order error. And we also need a gluing argument. So remember that the epsilon symmetry is only defined for a fixed size of parabolic neighborhoods, but this L0 is supposed to be large. So this statement or assumption really just tells us that we have a lot of rotation vector fields that represent the symmetry in different points, but we don't have a single one that could represent symmetry for each point. So the gluing argument says that we can actually achieve that. We can actually use only one vector field, but the price to pay is that we pick up a huge constant here. However, we could have some good control after adjusting u by some phi1, that is near any point in this parabolic neighborhood, we could adjust k slightly or adjust u slightly by phi1 such that u is much smaller. And then with this thing set up, we can do some analysis of the Jacobi equation under polar coordinates. So our geometry ensures that this equation would be very similar to those on the cylinder. So we will do the separation of variable by Fourier transform. We want to separate out the theta factor. So this equation would have the following modes, which is Pcm cosine m theta and Pcm tilde sine m theta. And Pcm and Pcm prime are just the equations they are not depending on theta. Each of them are the solutions of the Jacobi equation on the cylinder. And it turns out that this Pm has some good property if m is large. So if m is greater than or equal to 2, then, and also if Pm exists on a large backward parabolic neighborhood like this, suppose that this is the existence, or it should be like Pcm and Pcm prime. And if they are reasonably small on this parabolic neighborhood, then at the center, it will actually become much smaller by the factor of L0 to the minus alpha. This is for the higher modes. For the zero modes, we are able to show that it's always small. And there will be a bad mode, which is the first mode. But fortunately, the first mode corresponds to a geometric behavior, which is the tilting and translating of the axis of the vector field K. Therefore, we could just adjust K to annihilate these bad modes. So with these facts being packed up, we arrive into a conclusion that we could adjust U by phi1 such that the adjusted function will be much smaller than epsilon. And this adjustment is just a representation of the adjustment of K by some rotation and some translation. Therefore, that means we do find another rotation vector field K tilde such that K tilde dot nu will be very small, will be much smaller than before. Well, we have ignored the factor of h, but we have to multiply it up when we carry out all the computations carefully. Anyway, this just gives you a rough idea of what is happening. Then look at the right-hand side of this quantity. This is very good because it can be made to be much smaller than epsilon. So first we take L0 to be large to overcome C, so that the coefficient here is much smaller than 1. And then we can take epsilon 0 to be even smaller to overcome CL0. And then this constant is also small. So to sum up, we do get a much better estimate. So that proves this lemma. The next, we need a second symmetry improvement. The statement is that there exists a small epsilon1 and large L1 that are based on the previous constants, such that if this huge parabolic neighborhood looks epsilon1 close to bow cross R, and every point is epsilon symmetric, then the center point is half epsilon symmetric. So the statement is exactly similar except for the two difference. One is we need to take a much smaller epsilon1 and much larger L1. The second is we only consider the parabolic neighborhood that resembles bow cross R instead of S1 cross R2. So here's the idea of the proof of this lemma. First, what we do is we need to iterate the previous symmetry improvement to show the following statement. If a point is getting further away from the tip line, then it should be more symmetric. So this tip line, remember that there is a unique tip for the bow soliton, and this tip will become a line in the bow cross R. So the picture should look like this. And this we will call it L. And after rescaling, this statement is saying that if one point X, it has huge distance, dxl, then, or we have the precise quantity here, 2 to the j over 100 lambda, then we would have that X is 2 to the minus j epsilon symmetric. The next thing is similar to the previous lemma, that we need to find a single vector field K that realizes the symmetry. So remember that the symmetry, each vector field can only take responsibility for a fixed neighborhood size. So we need some gluing arguments to show that these vector fields, which takes responsibility for difference over neighborhoods, doesn't deviate too much. So it turns out that we can pay the price of this constant and then use the single vector fields to represent all this symmetry. This C will change from line to line, but they are always small and they are always in between 1 over 10 and 1 over 100. And so it's very technical, so I don't want to make this constant very concrete whenever not necessary. So the last step is to construct a barrier to make the center point very symmetric, or this U very small. So it's the best to draw a picture to illustrate how it works. So we have MT looks like bow cross R. So at time T, we have such picture. And the previous statement says that if we are getting far away from the line, then we are able to get more symmetry. So I would call this to be the boundary 1. And I would call this boundary to be boundary 2. And I would call the other boundary, which corresponds to an earlier time, to be the boundary 3. So we should have similar picture, but the picture should have been shifted to the left. So this corresponds to the time t minus 2 to the cj, where c is something that I don't specify here. So this is the boundary 3. So this entire thing is 3. So now we construct a barrier on this parabolic neighborhood. So the barrier is denoted by V, and we would require that V overcome the upper bound that we have obtained before, yet U is very small near the base points, so that we can control the U near base points. So the last key thing is that V has to be a super solution of the Jacobi equation. So it turns out that such a V exists by a careful choice of the size of the neighborhoods. And then we are done. So like these two things means that V is greater than or equal to U along the parabolic boundary. And since V is super solution, U is a solution, then the first bound would imply that U also is satisfying such a bound near the base points. But that's exactly what we want, because we just want U to be a bit smaller than epsilon near a fixed neighborhood of xt. And this is the basic idea of the proof of the lemma 2. Next is the proof of the main theorem. So we first need a canonical neighborhood theorem. This theorem roughly says that if we have a unique tip that attains the maximal mean curvature, and then if a point is sufficiently far away from this P, or away from a compact set around P, each point is sufficiently close to either one of the model. So we can quantify them by L1 and epsilon 1 as shown here. Since these two models are already symmetric, then we can also obtain that these points away from a compact set is already epsilon 1 symmetric. So here is the picture. We have the unique tip here, and then away from a compact set, each point, for example, centered at here, there should be an open neighborhood that looks like either one of the models. So for example, here it should be along the edge, should look like bow cross R. Whereas in the more interior region, we should have S1 cross R2, S1 cross R2. So that's the rough picture. Let me also mention what happens in the uniformly 2 convex case. In that case, the canonical neighborhood theorem is much simpler, but I would just give a brief version of that. So roughly speaking, it says that on an ancient solution, there's a P that attains the maximal curvature or the mean curvature, and then around this P, it should look like the bow soliton. But away from this compact set, it should look like a neck. So every point here, there should be a neighborhood that looks like S1 cross R2, S2 cross, Sn minus 1 cross R. That's what happens if we assume a better convexity. Then we follow exactly similar step as the work of Brendel and Troy. The first is that we would iterate the symmetry improvements, either one or two, to obtain the following conclusion, that if the point is getting further and further away, then it's getting more and more symmetric. And then we would find, using the gluing arguments, a single vector field that realize 2 to the minus a half j epsilon symmetry. So note that during the gluing argument, we would always lose some constants, but these constants are always controllable. And then the last step is to construct a barrier such that it overcomes the bounds we have obtained on the parabolic boundary, but it is enough small near the points under consideration. With this, and also most importantly, V is a super solution of the Jacobi equation. With this construction of V, we are able to control U near the point P, and so it looks like U is less than or equal to 2 to the minus a quarter J epsilon 1 near an arbitrarily large neighborhoods of P. And there could be some other constant multiplied in front of 2 to the minus J or 4. But this constant doesn't depend on J. And then we can pass to some limits and find a single vector field such that it is actually tangential in this way. But this means that it is actually a killing vector field on the hypersurface. And our goal has been achieved. Remember that we only need to find such a rotational vector field, which is a killing field on MT. And then this completes the proof. So that's all what I want to talk about. Thank you for your attention.